No surprises here, but I've seen my fair share of sci-fi movies. Nerds unite. There's something about the laser battles and CGI spaceships and the generally epic soundtracks. You could say I'm something of a science fiction nado, but there's one trope, one plot device, one thing that almost always leaves me with more questions than answers. Black holes. They're like the all-around go-to in sci-fi. They can act as a wormhole that somehow conveniently links two distant bits of the universe for space travel. Or they can become a dark, hungry space monster that gobbles down everything in its vicinity, which sounds like a fitting description of a lot of people come Thanksgiving. But let's get away from that mental image and talk about Interstellar instead.
Approaching the event horizon. Port side, dipping down beneath it to go through it. Heading towards blackness. I'm visually. It's all black. Tars, you read me?
From the scientists I've talked to for this podcast, Interstellar is not only a favorite sci-fi movie.
One of the movies that I enjoyed most was actually Interstellar.
I am very fond of Interstellar.
I do love Interstellar.
Interstellar offers us the most accurate cinematic depiction of black holes we could hope for. I mean, after all, they did consult theoretical physicist Kip Thorne.
Gravitational pull, I'm losing control. Stick.
I want to believe Matthew McConaughey knows what he's talking about. I do, I'm on his side. But still, this is a made-up movie. So how much do we really know about black holes? And how much do we think we know? Today on Nova Now Universe Revealed, we're taking matters into our own hands and journeying straight into a black hole to find out just how much is fiction and how much is reality. And here, reporting for duty as your co-pilot, I'm Alok Patel.
In some sense, black holes are places, not things. And that's very attractive to me. It's much less gooey and messy and sloppy. So there's something about the purity of the empty spacetime of the black hole that's very intriguing.
Jana Levin is a professor of physics and astronomy at Barnard College of Columbia University. She's also an author and general black hole enthusiast. And Jana agreed to take me on a journey into a black hole, specifically the supermassive black hole at the center of our Milky Way galaxy. So I was wondering if you and I could play like sci-fi movie and we could pretend that we're in a spaceship and we're ready to head off to the center of the Milky Way to go to the black hole. The first thing I need to know is, what are we going to call our spaceship?
Gosh, I don't know. I mean, there's this cute trick that when we name black holes, we name them with a star. So our black hole is called Sagittarius A, because it's in the direction of the constellation Sagittarius from our perspective. So I think we should call our spaceship something like Milky Way star.
Milky Way star. I was gonna put Jan Lev star in there to try to give a nod to you.
Oh, you know my animation name is Jan 11, like Jan 11.
Oh my gosh! All right, so it's gonna be a play. So our spaceship, the Jan 11 star, is now heading towards the theoretical black hole in the Milky Way. If you had an educated guess, how far roughly is this from us? I mean, I'm saying 25,000 light years, but...
Yeah, it's between 25 and 27,000 light years away from us. So if we traveled at the speed of light, we would get to the center of our galaxy in 26,000 light years. Let's just land in the middle.
So we're traveling for 26,000 years if we're going the speed of light, which we can't yet do. So I'm assuming that we have brought snacks and cards and games to play for this extended period of time. What is happening to our view around us as we're getting closer to the black hole?
I think people often think of black holes as these big megalith monsters, but actually the whole point is that they're small for their heft. They're actually really hard to see from far away. So the black hole Sagittarius A star is only about 20 times the width of the sun across. If you picture the sun on the sky and you imagine 20 times larger and then you push it to 26,000 light years, that thing is as small as a piece of fruit on the moon from where we're standing. So you don't see a lot until you get very, very close. You have to get really up in its face. And then you start to see that it's bending the shape of space-time, and so the path of light is bent around it. And so it's like a lens. It's like you only notice it's there because there's a shadow and because it's causing the distortion of things behind it. That's the only reason you know it's there.
Since we have 26,000 light years to travel, we've got a few minutes. To wrap our heads around black holes, we first need to talk about space-time. Not space and time, but space-time, one word. The idea of space-time is part of Albert Einstein's theory of special relativity. In this theory, space and time are woven together into a four-dimensional fabric called space-time, with 3 dimensions of space and 1 dimension of time. Connecting space and time isn't actually that foreign to us. Think about every time you've made a plan to see someone. You have to agree on both a place to meet up and a time to be there. Jana and I agreed to meet on the Jan 11 star spacecraft right now so that we could journey into a black hole together. If we hadn't agreed on a time, Jana might be in the middle of teaching one of her classes. And if we hadn't agreed on a place, I might be light years away from Jana by now. Simple enough, right? But get this. Not only are time and space woven together like a fabric, that fabric is flexible like a trampoline or the skin of a drum, capable of being stretched or bent by objects with mass or energy. One familiar example of the bending of space-time is gravity.
The funny thing about gravity is we think it's such a dominant force in our experience, but it's actually really, really weak. I mean, the whole Earth is pulling on me and I can still lift my water, you know? It requires incredible concentrations of mass and energy to notice that things are deforming space and time. But the idea is that, matter and energy curve space and time, and then that space-time tells everything else how to fall weightlessly and freely around those curves in space and time. So one way to think of it is like this. If I were to take one of these books off the shelf and I was to throw one of them, we know it would not travel on a straight line. And during the time that that book is falling freely, uninterrupted by the floor of my office or by a chair, anything else getting in its way, during the time that it's falling freely, we know it traces a curved path. And that should be the first observation that it's following a curved trajectory in space-time, which is crazy. I can literally go around the globe throwing things and everything will follow arcs and curved paths, and I can map the shape of space-time around the Earth that way.
The gravity we experience on Earth is weak enough that we can lift objects or walk around or slam dunk on the b-ball court. But a black hole is a place where gravity is so intense that not even light can escape. And the gravity gets that strong because an incredibly large amount of matter has been squeezed into an incredibly tiny space. So what do curves in space-time have to do with black holes? Let's start at the moment a black hole is born. One way scientists believe black holes are created is through the death of certain stars.
So imagine a star is collapsing under its own weight. At some point, it does get so dense that it creates a black hole. And what we really mean by that is that it has deformed the space-time around it so substantially that it has left, almost as an archaeological imprint on the space-time behind it, a curve so deep that not even light can escape. It would have to travel faster than the speed of light to escape again. And it can't do that, and nothing can do that, so it falls in. So it leaves an emptiness behind. Not even the light from the star is there. The black hole is just an empty shadow, and there's no more there in the shadow than there is in the shadow of a tree.
You said early on that the way we can tell
we're approaching the black hole is not necessarily because we see this pitch black, ominous, beautiful object or lack of object, but we see light bending.
We see a shadow and the light bending around this darkness. So if you saw the image that was released in 2019, which is the first time we've ever actually seen an image of a black hole, which is an absolutely stunning human achievement. Shep Doeleman of Harvard was the PI on the Event Horizon Telescope project and drove that forward. It took him 20 years. It was a real labor of love.
We are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is.
That's Shep Doeleman unveiling the first picture ever taken of a black hole. It looks like a bright, fiery, glowing blob with a dark circle in the center. Kind of like a fancy artisanal space donut. I'm looking at the picture right now and it's beautiful and kind of scary at the same time.
And what they took a picture of was the shadow, right? So just like a tree's shadow in midnight, there's no such thing. You can't see a tree's shadow in darkness. You need to have some source of light. And so what they looked for was the bright light around the black hole casting the shadow.
When material falls towards the black hole, the matter and light spiral around it like water going down a drain. This creates a bright ring around the dark black hole in the center.
And in the rim of that bright light, you see this utter darkness, which is the empty space of the black hole event horizon.
What exactly is the event horizon? That's the point at which the shadow is cast?
It is an empty region of space at which you would have to travel faster than the speed of light to escape. And it's like saying, what's the shadow of a tree? It's not like there's a thing in the shadow of the tree. It's just the region where light doesn't penetrate.
All right, we've now traveled most of our 26,000 light-year journey. As we get closer to the black hole, we see the light bending around it, leaving a dark shadow. But since we aren't yet at the event horizon, we're still safe in our spacecraft.
So you can safely set up an orbit on a bent path around a black hole. And it's very convenient that black holes bend space-time, as does the Earth. The reason why the International Space Station is in orbit around the Earth is because the Earth has curved space-time in such a way that we can find a circular curved path around the Earth. It's fantastic. So we love it. We send spacecraft up above the Earth, we turn off their engines, and we let them free fall. They just always clear the horizon and they travel on a curved path and they never hit the Earth, and they're not burning any fuel whatsoever. They're just literally just free falling. And so similarly, you can do the same thing around a black hole. You can safely orbit a black hole. It's completely fine, and that's the benefit of the curved space-time.
My other question is, as we start to get closer to the black hole, what is happening to our speed of our spacecraft? What's happening to the speed of matter around us as we get closer?
So let's say you and I are in orbit in the Jan 11 star spacecraft. And we're arguing and you throw me out of the spacecraft and I fall into the black hole.
Or vice versa. Or
I throw you out of the spacecraft.
Hey, wait!
We will start to notice that our very excellent Swiss watches that were designed to be totally not lose a second and are accurate begin to fall out of sync. So you're approaching the event horizon of the black hole, your watch will begin to look really lagging behind mine. But your experience of time is completely natural. It's not as though you think time is slow. It's not like your biological clock is immune from the same physical consequences. This is a completely real slowing of the passage of time for you relative to me. So you will be like metabolizing food really slowly. Your neurons will be firing really slowly, not for you, but just from my perspective, I'll be wondering what is going on with you. And similarly, I'll look like I'm very sped up. And The funny thing is that you have to get really, really close to the black hole for this to be extreme. And the closer and closer you get to a black hole, it can get to the point where 2 minutes have passed for you and 20 years have passed for me.
Whoa. Okay, so how far away from Sagittarius A star would this be happening? You said it was a very, very, very close.
Very close. You'd have to be right on top of the event horizon.
So if I jumped into the event horizon and then I came back out 6 minutes later, you would be 60 years older.
Yeah, you can't jump into the event horizon, but if you get like agonizingly, dangerously close, but do not cross it. And then you burn an incredibly expensive amount of fuel to get back out. Yes, I could be 60 years older and you could be 2 minutes older. And you would look at me and I'd be old. I would be like crazy old and it would be real. And I would have grandchildren and great-grandchildren and that would be real. You know, they would have new lives and they'd have gone to college and they'd have had experiences and you'd be 2 minutes older. That's real.
I'm literally speechless right now because I'm like, oh my gosh. But okay. And then in this moment when I'm dangerously close, would I feel something about like a suction or a force pulling me into the event horizon?
It's actually another one of these myths I love to dispel. Black holes are pretty harmless. Like, if you think about the curvature of the Earth, you hardly notice it walking around. You don't notice it at all. But the smaller a curved object you stand on, the more, if you stood on a basketball, you'd definitely be struggling to balance, right? So black holes are similar. The bigger the black hole, the less you notice. You would drift across the event horizon and nothing would happen to you. The smaller the black hole, the more likely you would feel the effects, just like the basketball. You would feel that you were being like, oh man, my left foot and my right foot are not on an equal footing, and I'm starting to feel the pull differently from my head to my feet. So weirdly, the bigger the black hole, the less you notice it. At least initially, you're in real trouble once you're inside.
Okay, this is the space where we say it's time for a quick break, after which we'll get into that real trouble. The point of no return when we return. Welcome back aboard the Jan 11 star spacecraft, safely orbiting the black hole at the center of the Milky Way, known as Sagittarius A star. Before the break, Jana and I were talking about the event horizon, sometimes referred to as the point of no return, because once you cross it,
all the fuel in the universe won't allow you to escape the event horizon.
It's probably very dark in this black hole in the sense where there's...
Funnily enough, black holes can be bright on the inside, even if they're dark on the outside, because all of the light from the galaxy can fall in behind you. So it can be really bright on the inside. You can see the results of the climate change crisis. You can see civilizations come and go. You can see the election of 2024. You can see, stars be born and die, all in a flash of a microsecond for you before you're crushed to death in the center. So it can be very bright on the inside.
Before talking to you, I was scared of black holes, and now I want to dive into one of them. Black holes might be bright on the inside and dark on the outside, but there are occasions when supermassive black holes create powerful jets of radiation and particles that shoot out in narrow beams. I mean, if light can't escape a black hole, where do these bright jets come from?
So the black hole is like sharks swirling around in the water, creating waves. It's not that the shark is disgorging water. It's that it's churning up water and it's creating waves. And so the black hole is churning up electromagnetic energy and it's creating a source of power and energy. None of the matter originates from inside the black hole. It all has to come from outside the black hole. So it's disrupted stars, it's torn apart other solar systems, and it's throwing them out into these fantastic jets. But again, none of it comes from inside the black hole. The irony is that the darkest phenomenon conceivable in the universe becomes the brightest beacon in the actual universe.
This is so wild. So, I can't help but now start to think about some of the concepts of black holes we've seen in science fiction television. And, one thing I have to ask is the whole concept of a wormhole, which it sounds so bizarre to me, but is it even theoretically possible that black holes can somehow transport matter to another point in the universe?
Wow, so that's gone all over the place for 100 years. And this is what I love about theoretical physics, is it's okay to dream and to be wrong, and then it sits on the shelf like a great book for a while, and then it comes back again. And somebody's like, wait, didn't somebody say something about this 70 years ago? And this is kind of what's happening with wormhole physics. So the way to think about it is, like, I'm right now on the 5th floor of a building at Barnard College, and there's a wormhole which exists to get me to the 4th floor. It's called a stairwell. And if that wormhole didn't exist, I'd have to go a long way around, right? But the wormhole's like a little shortcut somebody built for me. Now, we actually think that there are these black hole wormholes which are quantum.
Quantum, which relates to the physical behavior of very, very small stuff like atoms and subatomic particles. In quantum mechanics, two different particles can become entangled, meaning they're linked even though they exist in different points in space. This is known as quantum entanglement, but that connection on the quantum level might actually be able to act as a wormhole.
Maybe black holes actually emerge out of the entanglement of a bunch of quantum wormholes. And that, in some sense, the black hole isn't the fundamental thing, but the wormholes are the fundamental thing. From our macroscopic perspective, we think there's a black hole. But when we come up close, we realize, oh, it's just layers and layers and layers of quantum wormholes.
It's amazing how everything and anything is potentially possible here. One question I forgot to ask you, you talked about light and how it could potentially be bright. Do black holes inside, do they sound like anything?
Oh, black holes sound like something from the outside for sure. So we have recorded the sound of black holes. One way to imagine is, so if black holes curve space-time, then if they move, the curves in space-time have to follow them. And because of the limit of the speed of light, they can't follow faster than the speed of light. It takes them a while, right, to catch up to the moving black hole. And so what's actually created is if a black hole moves, there are waves in the shape of space-time as the curves in space-time try to catch up to the black hole.
When a black hole wanders close to another black hole, they become engaged in a gravitational dance until they eventually merge. As they orbit around each other, they not only curve space-time, they create waves within it.
And these two black holes are like mallets on a drum. They're creating waves in the shape of the drum of space-time. And those waves are basically unimpeded because gravity is so weak. So, like, let's say you create a curve in the shape of space-time and it begins to wobble in response to the motion of the black holes. It could travel wobbling and traveling like that. We call them gravitational waves. And in fact, we record them very much like you would record the ringing shape of a drum. And we play it back as sound, because that's the natural translation. Fact is if you sit in the control room of these experiments, which is the main one is called LIGO, there's also Virgo, and there's also Kagra, that trio of experiments around the globe, play them back in the control room through conventional speaker systems.
Oh my.
Like, you can listen to the machine, and you can listen to the first discovery in 2015 of black holes ringing the shape of space-time. It happens by coincidence to be in the human auditory range. LIGO, this instrument, is famously sensitive to the same range of frequencies that the piano plays.
LIGO stands for Laser Interferometer Gravitational Wave Observatory. Listen to the sound of the gravitational waves caused by two black holes merging, captured by LIGO in September 2015. As two black holes close in on each other, circling faster and faster, both the frequency and amplitude of the waves they create increase. Translated to audio, this means the pitch and volume of the sound increase. So as black holes merge, the resulting sound resembles little chirps. Ironically, these chirps might sound small, but they're the result of a huge and powerful cosmic event.
That first detection in 2015 was the most powerful event human beings have ever observed since the Big Bang. And none of it came out as light. All of it came out in the ringing of the shape of spacetime, which we recorded. By the time it got here, it was painfully quiet, which is why the experiment was such an achievement. But it was one of the most energetic events in the history of the universe.
I was going to ask you what all this knowledge about black holes, what it means for us here on Earth, and how we're applying it to other questions. 2015, that moment had to represent something very important in terms of our understanding of black holes, but also what it means for us to be studying them.
I love that question. So it was August, right before the event was recorded, and Ray Weiss, who has since won the Nobel Prize and was one of the major architects of the instrument, had spent 50 years of his life on this. And the first instrument was built in 2000, and crickets, right? 15 years later, they installed the advanced machine. We're on the eve of the advanced machine, and he says to me, if we don't detect black holes, this is a failure. And it's such an honest, painfully honest statement from a scientist who's devoted literally his whole life to it. It was a labor of love. It was a labor of curiosity. So it's just something about the human ambition. Why do we go on hikes? Why do we want to look from the top of a mountain at a view? Why do we want to know things? Why do we want to read books? Why do we want to write books? Because that's who we are as a species. We might be a complicated, failed species, but that's probably our best side.
So now I went against your advice. I was like, I'm on Jan 11 star, but I'm going into this black hole. So I dive into the black hole. You say, don't do it. I will never see you again. I say, but I must do this in the name of science. So what happens to me? What happens to matter, to bodies?
So if you fall into a black hole the size of the sun, you have microseconds before you begin to notice on the interior that your feet are being pulled more strongly than your head, and that you're being crushed towards the singularity, towards the center of the black hole. The singularity is hypothesized, and even if it isn't real, a region of infinite curvature, infinite gravity, infinite density, even if it isn't real, it's definitely the case that as you approach that special point, the curves in space-time become very extreme.
Simply put, singularities are places where our laws of physics and math break down. Like how dividing by zero has no answer, it's undefined. Gravitational singularities are places where the gravity, density, and curvature of space-time are infinite, which basically means it's gonna be a bumpy ride.
And so you begin to become flayed. You would be torn apart, your ligaments would be torn.
As I fall into the black hole, feet first, the gravity pulls more forcefully on my feet than my head, causing my body to stretch out longer and longer until I'm elongated into a string 1 atom wide. It's a process fittingly referred to as spaghettification.
You would be ripped into your fundamental particles, and then those fundamental particles would have to find their way towards the center of the black hole. In fact, find their way is really the wrong way of saying it. They would be forced towards the center of the black hole. The center of the black hole is as inevitable as the future, because the black hole, in some sense, has switched the placement of space and time. So from the outside, what we point to as the center of the black hole, for a person on the inside, is a point in time. It's the future. And they can no more avoid the singularity or whatever's in the center than they can avoid the next moment in time.
Nova Now Universe Revealed is a production of GBH and PRX. It's produced by Terence Bernardo, Jenny Cataldo, Ari Daniel, Caitlin Falds, and Jocelyn Gonzalez. Julia Court and Chris Schmidt are the co-executive producers of Nova. Suki Bennett is senior digital editor. Christina Monin is associate researcher. Robin Kazmer is science editor. Robert Boyd is digital associate producer. Shyla Duff is digital video intern. And Devin Maverick Robbins is managing producer of podcasts at GBH. I'm Alok Patel. We'll be back next week with our final episode of the series, looking way back to where it all began, the Big Bang. If you love stories about our universe, visit pbs.org/Nova Now podcast. And check out Nova Universe Revealed, a 5-part film series about the same topics we're discussing right here, like mysteries of black holes. You can check it out streaming now on the PBS video app. Visit pbs.org/Nova. This podcast has been made possible by the Gordon and Betty Moore Foundation.
GBH.